All right, recording is rolling. So welcome to another Monday, April 10. We're going to take the next few days to do some Kahoots on conceptual questions related to material and electricity and electromagnetic induction that you guys have been learning over the last couple of weeks. Okay? So today we're going to do electrostatics and electromagnetic induction, which is actually like the first thing I touched on with you guys, and then the most recent stuff. You guys remember like the balloon and the like tearing the tape apart and the Van de Graaff generator, that's like electrostatics. Okay. And then electromagnetic induction is the most recent stuff. Remember, you guys were like building motors and electromagnets, and you guys were doing that back on well, for the weekend. Okay. All right. Then Tuesday, Wednesday, I'm going to do all the middle stuff with you guys. So like current and circuits, conceptual questions related to those. All right. Now I have all these questions that you guys see today are all posted to Google Classroom. I posted them over the weekend, so if they're there, you can access them. You can see what questions they are. Right? But the ones that we're going to do Tuesday and Wednesday, I printed out. I'll give these to you guys tomorrow, just so it's one last day to hang on to these and keep track of them. But again, the questions are already on Google Classroom if you want to check them out there. Right? We'll do review on Thursday, and then Friday I'll get you guys an electricity quiz. Okay. The quiz is going to be open notes. Let me write that. Let's do open notes. I really don't think it's going to be that hard. I think you guys should do good on it. You know, as long as you've been studying and following along. A lot of the questions are going to come out of next couple of days of Kahoot questions, conceptual questions, which again, you guys will have those to follow along. So you guys be all right. Okay. And then I'll ask you just a few basic circuits questions that, again, if you guys have been following along, you guys know like parallel series, how current and power and all that work. You've been paying attention. I think you're going to be all right. Yeah, thank you. Okay. All right, so you guys get there? You guys know what we're doing? All right. So switch my screen over. You guys brought your laptops, which is awesome. Right, so we can do these questions here. If you forgot to bring your laptop today, of course, you guys know next couple of days we're doing Kahoots. So be bringing in your laptop this week. All right, here we go. Electrostatics. The charge of an electron. Is negative. There you go. Charge of an electron is negative. Points on the board. Protons and electrons. Attract. Yeah, attract together. Right? You guys remember opposite charges attract and then like charges will repel. So electrons repel, protons, electrons attract. Right? You guys remember I took those two tapes, tore them apart, and as they brought them close to each other, they started attracting because each tape had the opposite charge. Right? Have to start out neutral, so they'd have to have opposite charges. They would attract. All right. The fundamental force underlying all chemical reactions is what? Yeah, electrical. Right. So think about how the periodic table is organized. The number of electrons in the outer shell, like you guys remember learning in chemistry about like valence electrons, that sort of thing, right? So the number of the electrons in the outer shell usually determines how it will interact with other types of atoms, so like chemical reactions. For example, the noble gases have full outer shells of electrons, so they don't really want to interact with anything. Carbon has spaces for like up to 4 things it can interact with, so things like that, right? So electrical, thinking like what's going on with the electrons, how many electrons in the outer shell, right? Electrons and electrons, those electron fields can interact. Coulomb's law says that the force between any two charges depends on, oh, there's Coulomb's law right there. Yeah, both the above, right? So directly on the size of the charges. So if you increase either charge, then the overall force will increase. Right? But also inversely on the square of the distance between the two charges. And that was the same as universal gravitation. So like if you, here, for example, double the distance, because what happens if you double the distance? What happens to the force between them? 1/4 as much, right? Because 1/2 squared, right? That's true for electrostatic force. And that was true back in the day also for gravitational force. Right? Coulomb's law looks a lot like Newton's universal law of gravitation. Two charges separated by some distance. If the magnitude of each charge is doubled, what happens to the force on each charge? Ooh, quadruples, right? So if you double each charge, what happens to the force on each charge? Okay. Let's come over here. Let's look at Coulomb's law again. Okay. So I got two charges. Now, the example here, they're opposite charge, which means they attract. If they were the same charge, they would repel. But okay. but this magnitude, this force magnitude would be the same, right? Regardless. Okay. So if you, so the premise of the question is, if you double this charge and you also double this charge, it's a factor of 2 times a factor of 2, right? So the force would be 4 times as much. Guys, are these always the same force, or can they ever be different? Exactly. They're always the same force. Newton's third law. Isn't this a Newton's third law pair right here? Equal and opposite reactive force, right? Right? Yeah. So double each charge and the overall force quadruples. Factor of 2 times a factor of 2. When the distance between two charges is cut in half, what happens to the electrical force between those charges? Uh, okay. So only if you guys got this. Tell you what, this is exactly the opposite scenario of an example I just threw you guys a minute or two ago. Right. So a minute or two ago, here, let me give you guys a simpler version of this. Right. What if you double the distance between two forces? Here, let's flip over here and think about this. Right. So what if you double the distance? So this distance gets bigger. Now, first of all, if the distance is getting bigger and bigger between the two, is the force going up or going down? Yeah, it's going down. It's getting weaker, weaker, weaker. Right. That was the same as universal gravitation. Think about the force between you and the Earth. Think about the force between you and the say Mars. Right. Mars is so far away. Now it's negligible force. Right. Okay. So the greater the distance, the less the force. Right. And what if you specifically double the distance? What's a factor of 2 squared? 4, but that's in the denominator, so it'd be like a quarter of the force. Right. Now the way the question was just thrown at you is the exact opposite of that. If you turn around and cut the distance in half, well, that's also the opposite process. So the force would have to quadruple. Right? Okay, let me walk you guys through the solution here. So what if you have a charge here, call it Q, a charge here, call it Q, maybe the same charge, they don't have to be, but right. And then there starts off some distance between the two. Maybe I'll call it a D for distance, right? Right. And then the initial force, right? So force is equal to K Q Q over distance squared. Right? Maybe if they were both the same sign, also it would repel. But let's just focus on the magnitude, right? Let's say that's the original force, right? And then we're going to do. Let's have a new force that's K Q Q. So the charges don't change. Electrostatic constant doesn't change. Okay? But we're going to take the distance and cut it in half. So I'll have half the distance, right? And that's going to be squared, right? Well, that's like K Q Q over, see, 1/2 D quantity squared. It's not like a quarter of D squared. Okay. Guys, what is 1 divided by a quarter? Is that like 4? The 4 comes back out on top. K Q Q on distance squared. Would that be true? All right. Okay. Which is like 4 times the original force. Okay. All right. So double the distance, you get a quarter of the force. Half the distance, that's 4 times the force. It's good process to review right there. Conservation of charge. Yeah. So all those statements are true. But, different perspective on conservation of charge. Now, charge in the universe is constant. You can't create or destroy charge. If there's a single charge lying around, then same thing. You can't just be created or destroyed. And an application of conservation of charge actually led to Kirchhoff's junction rule, right? Like if there was like 10 amps coming in and it split at a junction, maybe it splits like 3 amps and 7 amps, but it has to add up to the same number of amps, right? To be safe in the unlikely case of a lightning strike, it's best to be inside a building framed with what? Uh, okay, steel. Now, why steel? Uh, It's actually a term for this called a Faraday cage. Let me show you guys that. Here you go. There's guys standing inside this cage made of metal and being struck with this electricity. And that's actually a pretty safe place to be because the electricity wants to, you guys know metal is conductive. So electricity wants to follow the path that is the metal path, the conductive path, down into the ground. Electricity would like to get to the ground if it can. Okay. Uh, Way back in the day, let's go back to like 1700s. So, but you guys know that lightning a lot of times like to strike tall, pointy things. So maybe like tall trees, maybe like a tall statue. How about like a tall, pointy building? Now, way back in the day, this was noticed that lightning would strike like church steeples or like anything tall, pointy like that. And it was Ben Franklin who invented what was called at the time a lightning rod. He said, "Hey, let's put a metal rod up there and let's route a wire all the way down to the ground, and that'll stop all these churches from being struck by lightning, catching on fire," which it did. And then the extension of that is, well, hey, lightning could strike like any building, so let's just frame the building in metal, and then we'll have like this Faraday cage, and that's a safe place to be. So actually, right now, sitting in this modern building, we're in a version of that, inside a version of a Faraday cage. So if lightning strikes the skull, we're going to be all right. Like the lightning's not going to strike us inside this room. If you're in a car right, during a lightning storm, you're usually pretty safe inside the car because if lightning strikes your car, okay, maybe like bust the windshield or something, that could be dangerous. But the electricity itself wants to follow the metal body of the car, so the car is also like a Faraday cage version of that. All right. Two charged particles near each other are released. As they move, the force on each particle increases. Therefore, what? Oh, yeah. The particles would have to have opposite signs right here. Show you guys a visual of that. Probably follow that, but just in case not. Okay. So say we're thinking about these charged particles, right? And here they are shown with opposite signs, which is like the answer to that, right? If they have opposite signs, that means that they want to pull together, which means they're going to get closer. And as they get closer, distance decreases, the force would increase. So that would be in line with that. Versus if they had opposite charges, then they'd be pushed away from each other, and then the force would decrease. Opposite situation. You guys get that? Two charged particles held near each other, released. As they move, the acceleration decreases. Therefore, what? Ooh, nice, nice, nice. Once everybody got that. The particles have to have the same sign. Okay. Just in case you're not following, I'll show you guys a quick explanation. Okay. So if these charged particles have the same sign, then they're going to push away from each other. Okay. If they push away from each other, then the distance is increasing, which means that the force is going down. And since the acceleration of each particle is force on mass, as the force goes down, the acceleration also goes down. So they're like slowing down as they go away from each other, right? You guys follow that? All right, good deal. The SI unit of charge is oh no, nobody got that. Okay, so let's go through all these. Most of you guys said amperes. Guys, what does amperes measure? Electric current, right? Amps, like how many amps are flowing, right? Isn't that voltage acting on resistance, like Ohm's law, right? And what character were we using to quantify how many amperes for current? Oh, that's the unit. So the unit is amps, and the character was capital I, capital I. You guys remember I was current? I was current that was measured here. Hold on. We gotta flip over to this. Okay. We go way back to the beginning here. Right, let's take a look at these. Okay. So electric charge, some version of Q, sometimes capital, sometimes lowercase, but whatever, is measured in coulombs. That's the answer, right? So charge is measured in coulombs. That's just a static charge. You just have like a static charge lying around, right? Take a balloon, rub against my hair. Right? That's some number of coulombs of charge on the balloon. Okay. Now, if you can get that charge flowing at some rate, that's what electric current is measured in amps, right? So electric current, which is I, measured in amperes or amps, right? That's like coulombs per second. Okay. Some other ones, you guys know voltage potential difference measured in volts, which is like energy per unit charge. Okay? Resistance in ohms was one of the options, right? That's Greek letter, right? Represent omega, right? And then energy is measured in joules, which I don't quite have a row for, but I do have power in watts, which is like joules per second. Right? Okay. Uh, questions on any of those? Okay, so charges and coulombs. Okay. All right. I think we did that one. Particles A and B interact with each other due to proximity. Particle A has twice as much charge as particle B. Compared to the force on particle A, the force on particle B is? Uh, the same. Yeah, the same charge. Hey, isn't that what law of motion is that? Newton's third law of motion, right? For every force, there's an equal and opposite reactive force. Okay? How about well, let's go back to gravitation from last semester. There's some analogies there. The force between the Earth and the Moon. There's a force between the Earth and the Moon, right? What pulls harder than the other? Does the Moon pull harder on the Earth or the Earth harder on the Moon? It's the same force, right? Equal and opposite. For every force, there's an equal and opposite reactive force when two objects are interacting, right? And that was true for gravitation, but taking this one, even if two charged particles have different masses or different charges in this case, it's the same force between them, right? They pull or push on each other with the same force. If they have different masses, they might accelerate differently, but same force, same force. Right? Two charges separated by 1 meter exert 20 newtons on each other. If the charges are pulled to 2 meters, now what's the force on each charge? Um, yeah. Okay. So if you double the distance, you get a quarter of the force. Right? A quarter of 20 newtons is 5 newtons. I flip over and show that to you guys on paper. I'll just show you guys the notes from last class on this. Okay. So suppose you had two charged particles and you ran kq over distance squared and count 20 newtons. We've got 20 newtons of force, electrostatic force. That was the original value. Okay. And then what we're going to do is double the distance. As you throw a factor of 2 on that d, 2 squared is like 4, so that's like 4. You can pull that out. It's in the denominator. Okay. And then all this stuff was 20 newtons. So a quarter of 20 newtons is 5 newtons. Okay. So double the distance, you got a quarter of the force. How to do? All right. Everybody good so far? Right. Oh, to the podium with the bronze. Wendy's Baconator with the silver. Haley and the gold. Oh, Mumfler Fumpkindink. Yeah. Trying to gonna make me read that. Yeah, so nice job. Oh, yeah. Nice job there. All right. So hold on. No, let's do that. Let's do this. All right. So we're good on that one. Let's line up another. Okay, we're gonna switch over to electromagnetic induction, which again is like the most recent type stuff we've been doing. You guys remember? Yeah. So we're just doing. It's also true tomorrow and the next day. We're gonna do more Kahoots. Okay. So just to remind you guys of context while you guys are signing up on that Kahoot right there.
How do you feel about this game, Tim?
Do what?
How do you feel about the game, Tim?
Oh, well, sorry. It is what it is. Numbers are random. How about that? Right? So you guys remember we started with electrostatics. I talked about it briefly with you guys, and then did current and circuits with you guys. We're looking at how circuits work, Ohm's law, Joule's law, resistors in parallel and series. Okay. And then finally, we ended last week talking about electromagnetic induction. So motors, generators, electromagnets, you guys built a lot of those things. Okay. That's the Kahoot we're doing right now. Now, current and circuits, I have more conceptual questions on those, and also have those questions printed out. And those questions are also the ones that are going to show up on the quiz on Friday, the one on current circuits. So we're going to save those for the next couple of days. Okay. All right. So almost in here. And so electromagnetic induction. And all these questions are posted to Google Classroom. They're there in a PDF. All right, let's get going. Source of all magnetism. Moving electric charges. There you go. Yeah. And so moving electric charge that will create a magnetic field. Right. Ooh, I actually do want to show you guys real fast. Here you go.
The source of that magnetism was being.
Let's skip to the part I care about here. Right. Right. Here you go. Yeah, you guys remember this?
Point north. But you know what would happen if I put a current through that wire? All the compasses will line up with the field. And it turns out that field, it takes the shape of concentric circles about the wire.
All right, there you go. And then one thing you guys did back for the weekend was if you run that wire around in a loop, like an inductor type shape, then that will create like a straight magnetic field, like a magnet, electromagnet. Moving electric charges will interact with yeah, magnetic field because it moving electric charges creates a magnetic field, so it'll interact with another magnetic field, and electric charges will already interact with electric fields anyway. So yeah, both of the above. An iron rod becomes magnetic when what? Yeah, the net spin of electrons points in the same direction. Right? I didn't actually tell you guys that, so awesome job if you guys figured that out. Now, right, so if you pick the blue one's saying, what if you have like more positive charge at one end, more negative charge on the other end? Like you have something like that, but that's not actually what a magnet is. Right? What a magnet actually, at least the main theory of what makes a magnet. I mean, we're talking about like atoms, so there's a lot of like weird quantum theoretical stuff with this, but has to do with electron spin. So if you can get electrons to spin in one direction on net, then that will create a magnetic field. If the north pole of one magnet is brought near the south pole of another magnet, those poles will attract. There you go. So north and south attract, opposite poles attract. If you break a bar magnet in half, each half becomes a bar magnet with two poles. There you go. One thing, I gave you guys a stack of bar magnets last week that constructed some things with. If you have a stack of magnets, then it essentially acts as one giant magnet, and then you can split that in half and then get smaller magnets out of that. Now, every magnet has to have two poles, though. I don't think there's anything in nature such thing as a unipolar magnet. So pole magnets always have a north and a south. When current passes through a wire, a magnetic field is created around the wire only if yeah, there you go. Magnetic field is always created around the wire. That was that Paul Hewitt video I just showed you guys, right? So even if it's like a straight wire, there's still a magnetic field. It's in concentric circles. Okay? Now, I did make a whole deal last week about putting that wire into loop, and that was just to straighten out the field and to make an electromagnet that had a clear like north and south pole to it. But yeah, there's always a magnetic field around a current. In order to make an electromagnet, you need, how'd you guys do it? Ooh, all right. Those guys got that. Awesome. Right. That's exactly the materials I gave you guys to make that electromagnet back before the weekend. So you took that wire, you wrapped it around and around and around that bolt. Sorry, nail, same idea. That created an inductor type shape. And then you hooked the leads of that wire to a battery, which with the voltage source, now it has a current going through it. And now you had an electromagnet with the north and south pole, right? So you don't actually need a permanent magnet to create an electromagnet. Okay. All right. Wire. Right. loops of wire in a motor rotate because all right. Okay, magnetic field exerts forces on moving electrons in the loop. All right, please skip over here and show you guys this. Yeah, so this is electromagnetic induction, right? Remember, generator and motor are like they're just mirror images going on here. They can be the same device, just they do opposite things, right? So remember, what a generator does is if you have a mechanical motion and you force a wire past the magnet. Now, it's hard to do that. There's a resistive force. That's like Lenz's law. You guys remember Lenz's law, right? Then that will create sometimes called electromotive force, like a voltage, create a current. Okay? A motor does the opposite thing. Right? So a motor will there'll be an electric current running past this magnetic field, and that will create an actual force, which will create a mechanical motion. Right, electromagnetic induction. Right. Magnetic field exerts forces on moving electrons. Moving electrons, that's a current. Right hand rule. Earth's magnetic field. Most likely due to what? Ooh, yeah, convection currents in the multi-part of Earth's interior. Okay. It should use, okay, only a couple of guys got that. So let me find the slide where I was talking about this the other day. So you guys remember this right here? Right? So the fact that the Earth is spinning, there's a molten mantle with ferromagnetic materials in it. Right? Put two and two together, right? Different latitudes, a Coriolis type effect probably going on, right? Put all that together, right? Right? If a compass is moved from the northern hemisphere to the southern hemisphere, the magnetic needle will do what? Yeah. All right. We'll change direction. Not at all. Okay. Only got half you guys got that. So let me draw this one out for you here. Okay. So here's the Earth. Say you had a compass in the northern hemisphere. Okay. Well, the needle is going to point to the north, right? Something like this. Okay. You guys know there's actually a giant south magnetic pole at so like south magnetic up here. In Antarctica, there's a north magnetic pole. You guys know that? Okay. The poles are opposite because back in the day, okay, well, some side of the magnet wants to point north. So we'll call it the north side. But then afterwards, there was, okay, it's actually opposites attract. So oops, right? But anyway, regardless, if you take this compass and change hemispheres with it, just move it down here into the southern hemisphere, right? How's that needle gonna move? Well, the north still points north, and the south still points south. So it doesn't actually move the needle, right? Still stays aligned. Magnetic field lines surrounding a magnet are conventionally drawn. Yeah, north to south, north to south. Okay. Give this a moment. Yeah. All right. All right. So magnet field. All right. And then, oh, look at that. See how the lines are drawn from north to south? Now that's just a convention people came up with, coin flip. It could have been either way, but that's what I went. But once you know what's north and what's south, then you have those field lines, and you can play out the right hand rule to assign directions to things. Like there could be a vector type direction of these magnetic field. Magnet moves in and out of a coil of wire. If the number of coils doubles, what happens to the induced voltage? All right. Also doubles. Right. Remind you guys what this is. This is Faraday's law. Faraday's law. Okay. You guys remember? Okay. So magnet, coil of wires moving in and out. Okay. The voltage that's induced, some textbooks use epsilon, so I just do that here. Okay. Is proportional to the number of coils. That's what N is, right? Number of coils. You guys remember that? Okay. So, and Paul Hewitt was showing this too. He said, what if I do one coil? What if I do two coils? What if I do three? Okay. And every time he added a coil, and he forced that past the magnet. So for every new coil, it would increase the voltage because the wire was connected to a voltmeter. All right. A magnet is moved in and out of wire connected to several lamps. If the number of coils is doubled, yeah, it is harder to move the magnet. That is related to Lenz's law. Here, let me remind you guys what this demo was. I had a better video of this, but got one here. Okay. You guys remember this magnet and this casing, right? It doesn't actually magnetically attract, but if it's in motion, then it takes forever to fall down. You guys know that, right? Because it'll produce eddy currents, which creates a resistive magnetic force, the whole thing. Right? But this is consistent with conservation of energy, right? So like if you double the number of coils, it's going to increase the voltage and therefore increase the current, but and the power, right? But that energy isn't created from nothing, right? So there's a resistive force that builds up. And it's get more resistive force with more coils. You do. Phenomenon of inducing voltage by changing the magnetic field around a conductor is called electromagnetic induction. There you go. That's the theme of this Kahoot, right? Electromagnetic induction. A lot of times I just abbreviated to EM induction. So that's what it'd be. Right? A device consisting of a coil that is mechanically rotated in a stationary magnetic field. What's that called? A generator. Ah, okay. Well, here. Flip over and remind you guys, generator, motor, these things are going to be here. Okay. So when they say a wire is mechanically rotated in a stationary magnetic field, okay? So you have some kind of energy source, maybe like this waterfall, for example, right? It's going to turn this water wheel. Right? That's a mechanical force. That's a mechanical input. Right? It might rotate this coil of wire. You guys see this coil of wire right here, right? In a stationary magnetic field. Right? That's going to induce a voltage, which creates a current. And now the energy's been redirected to like moving electrons, electricity, like electric energy. Right? Now a motor is like the opposite process. If you take that now electric energy and run it past the magnet, that will create a force, right, which will convert it back into a mechanical type energy. It could like turn a ceiling fan, for example. Right? You guys know that? Okay. You know, I should mention too, like this will work. I think I've seen this model too, and this makes more sense. This is probably how most commercial generators actually work. which might be involve like a spinning magnet, and then the wires are stationary, but a wire and a magnet have to move past each other to make this whole thing work, right? Some version of that. A device that transforms electrical energy into mechanical energy. Is a motor. There you go. Right? You guys get that motor? Just showed you guys that one, right? Run electric current past a magnet, creates a force. Boom. That's what a motor is. Most commercial generators are driven by most of our energy from.
I guess everything except for wind is full of water.
True. Yeah. Touche. Right. Yeah. So steam. Steam is what we're looking for. Right. So most energy still comes from fossil fuels. I think the energy power in this room right now, the air conditioning, the lights, the blah blah blah. Right. I think most of it's natural gas. Most natural gas. There's a bunch of coal. There's other stuff too. I think like 20% nuclear. But all those examples. So natural gas, coal, nuclear, all involve boiling water. That boiling water, steam. Now there's thermal energy that turns a turbine, which runs the generator, right? Forces a wire past a magnet. Boom, there you go. So that was called the Rankine cycle. You guys remember that? Back in the thermo section, talked about the Rankine cycle. A device that uses two coils around an iron core to change the voltage across a circuit. Big O, transformer. So go back over here. You guys. So you guys remember this? Now, say I have a red wire here and a green wire here, and they're not touching at all, right? But there's a current going through the red wire. Well, because this looks like an inductor, now it's creating a magnetic field. The green one picks up the magnetic field and it transmits that electricity like wirelessly. Okay? But if there's different numbers of coils, then the voltage drops down. Now, if it's high number here and low number here, the voltage is going to step down, in my case, from left to right, step down in proportion to the number of coils, right? The current steps up, but that side, right? It's conservation of energy, why one goes down, one goes up. Right? So the physics phenomenon is called inductive coupling, and the device is called a transformer. Ooh, got just enough time to knock out these last two. An electric motor and an electric generator are what? Yeah, very similar devices, right? They have the same component parts. They're just doing opposite processes of each other, but internal, they look about the same. Right? Oh, a step-up transformer. Ooh. All right, good call. Would increase the voltage, which is kind of the opposite of what I was just showing you, where from left to right it would step down the voltage. But yeah, if you increase the number of coils left to right, then that would increase the voltage. And that would be a step-up transformer. Transformers usually go from the electric grid, like 100,000 volts, to like a house to like 120 or 240 volts. Okay? I got third place, Shaboing Boing. Second place, the Whopper, and first place with the gold. Yeah. All right. Nice job, guys. Nice job. And that is a wrap on today.